Good day everyone, I am Rafael Miguel M. de la Cruz from the UST Philippine Nuclear Research Institute, and I'm going to present about the influence of metal reinforcements, boron carbide, zirconium oxide, and silicon carbide on radiation and interaction properties of reinforced aluminum 6061 composite. Aluminum has been an all-time choice in many industries because of its attractive properties such as being lightweight, high resistance to aqueous solution, and low neutron cross-section. In such applications, aluminum has been found compatible with industries of automobile, watercraft, and aerospace, and is mostly used in energy-related applications such as nuclear reactors. However, despite being versatile material, aluminum still has some weakness in its mechanical properties and a weak abrasion resistance, in which several techniques are employed to strengthen the properties of aluminum. Advancements in aluminum research are being driven towards to more mechanically stable and lightweight material that leads to the development of hybrid aluminum matrix composites. One study concluded that hybrid aluminum 6061 matrix composites with boron carbide, zirconium oxide, and silicon carbide of varying compositions have better wear resistance due to the mechanical properties of zirconium oxide and silicon carbide. Furthermore, several studies have reported that the addition of metal reinforcements to aluminum 6061 improve its mechanical properties. As mentioned earlier, one application of aluminum 6061 is for nuclear reactors, as a material for nuclear support structures. However, little is reported on the interaction of metal reinforced aluminum 6061 composites with radiation. With these improvements in the mechanical properties, the present study aims to investigate the interaction of charged particles, alpha and proton, and a photon with B4C, ZrO2, and SiC reinforced aluminum 6061 composites via computer simulation technique using software programs to compare its performance against unreinforced aluminum 6061. The simulation was done using a Lenovo ThinkBook 64-based PC with Intel Core i7 10710U CPU with a clock speed of 1.10 GHz, 6 cores, 12 logical processors, and 16 GB physical memory RAM. The stopping powers and ranges were computed using the ion stopping and range feature of Stream software, whereas the mass attenuation coefficient or MAC was computed using EPIXS software and is based on Electron-Photon Interaction Cross-Section 2017 or EPIX 2017 library and was developed by a team from the UST PNRI. For the different compositions of hybrid aluminum 6061 composite, the reference composition simulated was based on the work of S. Muzir and Dr. S. Sivaganisan, and its density was based on experimental density. The stopping power of the different reinforced aluminum 6061 composites against proton and alpha particles was simulated. It shows that the stopping power of the matrix and reinforced matrix for proton and alpha particles, in which it reached a maximum peak of approximately 0.5 and 1.4 mega electron volt per milligrams per centimeter square at 65 kilo electron volt and 550 keV respectively. It is also seen in the figure that there is an increase in stopping power for each increasing amount of reinforcement with the matrix. The increase in stopping power denotes that the mean energy of each particle loses its energy at a linear rate. It is also observed that the particles with higher energy have a lower amount of stopping power, wherein particles are freely passing through without a significant loss of their energy. The range of the both charged particles to the composites is almost similar due to the minimal differences in their densities. The distance traveled by the particle before coming to rest increases as the energy of the particle increases. The MAC shows that the different attenuation coefficients of the reinforced composites as a function of photon energy. Most of the interactions are due to the presence of zirconium oxide and silicon carbide. Likewise, the peak occurred between 15 and 200 keV where the value of MAC is increasing without the increasing content of zirconium oxide and silicon carbide. At the same energy range, there is a peak brought about by zirconium oxide component. It is also compared with the MAC of zirconium and silicon. Still, zirconium has more peaks due to the higher Z value among the two elements. Furthermore, the energy region at 1 to 10 keV where sharp peaks appeared is attributed to the absorption edges, wherein the energy of the photon is capable of knocking out electrons in different electron shells of an atom, depending on what energy of the photon and electron shell. and less likely to be associated with photoelectric interaction of photons with the material. In conclusion, the calculations conducted at different reinforced aluminum 6061 components showed that even in the maximum added reinforcements of 2% boron carbide, 6% zirconium oxide, and 12% silicon carbide, there is no significant improvement in their interaction with radiation. Thus, it has a low alpha, proton, and photon interactions in high energy regions. It is recommended that neutron interaction should also be investigated in further studies. In addition, the reinforced aluminum 6061 composite can be a possible candidate for suitable nuclear support structure material. Thank you very much for listening. This work was supported by the DOST Philippine Council for Industry, Energy, and Emerging Technology Research and Development under the project number 08669, Establishment of the PRR-1 Subcritical Assembly for Training, Education, and Research.